Welcome to Calculus 2. Today we're going to talk about improper integrals. We're actually going to spend, I think, 3 videos on this. We're going to start out by talking about improper integrals of type 1. So here's the definition. Any integral with an infinite limit of integration, you can see it like here, a finite limit to an infinite limit, a negative infinite limit to a finite limit, or a negative infinite to a positive infinite, is an improper integral of type 1. And here's the notation for them. And here's how you actually evaluate them. They all involve limits. So, if you have the integral from a to infinity of a function, that's going to be equal the limit as b goes to infinity of the integral a to b of your function. So you evaluate it as if you had a finite limit. You just leave a b in place, get your formula, and then you evaluate a limit. It's pretty simple. For our purposes, we kind of need it to be an elementary integral, but I mean, you could still approximate it. It just becomes harder because you're dealing with 2 levels of approximation. There's a very similar format for integrating a negative infinity limit. It's just the bottom goes to negative infinity instead of the top going to positive infinity. And if you have both limits being infinite, well, you just have to split it in the middle. And we'll actually look at kind of a shortcutted method for doing this, because the c is just any real number. It doesn't really matter where you split it, because if you recall, when you do the approximation, when you use the fundamental theorem of calculus to plug in the endpoints, this is going to be plugging c into your indefinite integral, and so is this. It's just this one's going to be plus plugging in c, and this is going to be minus plugging in c. So they're just going to cancel out, and the only things you're actually going to have to find are the limits. And then lastly, before we go into an example, so if the limit exists, we say the improper integral converges, and the value of the integral is the limit. So if we actually get a value from this, we say it's equal the integral. And if the limit doesn't exist, we say the integral diverges. And if it goes to an infinity, then we'll specify which infinity. So we'll say, if this comes out to be positive infinity, we'll actually say it equals infinity, but it still means it diverges if we say infinity. It still means it diverges if we say infinity. So let's do an example. So here's problem 11 from 8.8. You see we have a type 1 integral with an infinite upper limit of integration. So this is going to equal the integral from 2 up to b, limit as b goes to infinity, of 2 over v squared minus v dv. So we do the work for this. Let's see. Doing the indefinite integral of that, well, v times v minus 1. I'm thinking a partial fractions, because we have a rational expression there, easily factorable denominator. So let's see here. A over v plus b over v minus 1 implies 2 equals a times v minus 1 plus bv. So v equals 1, we will get b equals 2, and if v equals 0, we will get 2 equals negative a, so a is negative 2. So this is going to be the limit as b goes to infinity, integral from 2 to b of negative 2 over v plus 2 over v minus 1 dv. Really lost that one there. So let's see here. So that's going to be reorganizing my terms here. Limit b goes to infinity of 2. Might as well factor out that 2. 2 natural log of v minus 1, absolute value, minus natural log of v, which equals, from 2 to b. So that's 2, limit b goes to infinity of 2 to b of ln v minus 1 over v. I guess I really don't need absolute value since on this interval it really has to be positive. Alright, so this is going to be 2 times the limit as b goes to infinity of ln of b minus 1 over b minus ln of, let's see, 2 minus 1? Yeah. So 1 over 2 and that's going to get us, let's see, you take limit of that as b goes to infinity. The inside's going to go to be 1, so that's going to be 2 times the ln of 1 minus the ln of 1/2. Oh. There we go. ln of 1 is 0, so this is negative 2 ln of 1/2, which I'm just going to be simplifying to ln of 4. So that's the answer. Now, I'll point out something on this problem. This is a notation you can use if you want. A lot of people in calculus, when they're doing problems like this, instead of bringing this limit notation, what they will do, once they actually do the integral, and have this 2 ln of v minus 1 over v. What a lot of people in mathematics will do is, instead of using this notation, which is more accurate, is they will say this. They will say 2 to infinity. Now this is not really a proper notation because you can't really plug in infinity. You can just take a limit as you approach infinity, but it's a shortcutted notation for I'm going to do that, so I don't have to actually write all the limit notations, because we know as we approach infinity this fraction will go to 1 and this will go to ln of 1, so it just becomes 0. So a lot of people will just use this 2 times 0 minus ln of 1/2 then. And there's a nice little elegance to that notation, even though it's a little bit misleading. So you may want to use this one. It's okay though if you want to use the limits as you go. Alright, for the next problem, I'd like you to stop the video and try it for yourself. I'll give you a few seconds here, but then I'll pop in with the actual worked out solution. So go ahead and try it for yourself. And here's the solution. The only real tricky part is once we've done the integration, we got inverse tangent x over 2. We're doing the subtraction. Notice I used the new notation here, but I made a little note up here. Tangent inverse of 1 minus tangent inverse of negative infinity. Because 1 is because 2 over 2. Or the limit is a goes to negative infinity of inverse tangent a over 2. And you might think, well, inverse tangent of negative infinity is negative infinity. It is not. It is not. If you look at the graph of inverse tangent, that's right, I got my notations all over this thing, but that's okay. So we do an inverse tangent of, really, it doesn't matter, we can just look at x. We look at the graph, you notice it has these horizontal asymptotes. And if you look at the range of inverse tangent in the book, or look it up on the internet, it'll tell you the range of inverse tangent is negative pi over 2 to pi over 2. So as it goes to negative infinity, it approaches negative pi over 2. As it goes to positive infinity, it approaches positive pi over 2. So, as we go to negative infinity, inverse tangent goes to negative pi over 2, so 1 minus negative pi over 2, 1 plus pi over 2. Continuing on, our last example for today is going to be a type 1 integral with infinite limits on both top and bottom. This one's a pretty simple integral. Alright, I'll go ahead and split it up once, although again, this is not probably preferable. This is not really efficient notation, but you know, it works. So this would be negative infinity to c of 2x e to the negative x squared dx plus integral c to infinity of 2x e to the negative x squared. And then you just work this out. I mean, these would both have limits. You know, the limit as a goes to negative infinity of integral a to c of 2x e to the negative x squared dx plus limit as b goes to infinity of integral c to b of 2x e to the negative x squared dx. What I'm going to do is I'm going to figure out the indefinite integral, and then I'm just going to skip a little bit around. So let's see here. Looking at that, if we just had e to the x squared, we'd be out of luck because that is a non-elementary integral, but because we have this x in front, we ought to be able to do a substitution. I mean, the derivative of the exponent is almost what's in front anyway. So let's do u equal negative x squared. So du will be negative 2x dx. You could actually convert the limits as well. I mean, it just means you're going to flip your order. Well, I guess maybe not. If I put negative x squared in, this would be negative infinity and negative infinity. So maybe it'll go to 0. We'll see. It certainly doesn't have to converge. This becomes the integral of, I need negative du is 2x dx. So this becomes negative the integral of e to the u du, which becomes negative e to the u, evaluated from negative infinity to infinity. Oh, I haven't actually plugged in my u again, so this becomes negative infinity to infinity of negative e to the negative x squared. So if we think about what happens to e, so we got negative e to the negative of infinity minus, so plus minus a negative, so, well, no, I pulled the negative out, that's right. E to the negative infinity. This goes to 0 as the exponent goes to infinity, because if you think about this is 1 over higher and higher powers of e, you know, e to the negative 2, e to the negative 20, e to the negative 30, that's 1 over e to the 30th. The denominator is getting larger and larger, and the top is staying 1, so this would go to 0, this would go to 0, and 0 minus 0 is 0. So this is indeed going to 0. Again, that's not a great notation because you know, you can't really plug in infinity. It's more limits. If I follow this notation the rest of the way, we already did our integration work, so this would become limit as a goes to negative infinity of a to c of e to the, negative e to the u plus limit as b goes to infinity of negative c to b of e to the u. So that is, pull out the negative, limit as a goes to negative infinity, e to the negative x squared, so that becomes limit as a goes to negative infinity of e to the negative x squared. Let's see, that's subtracted that. I got my things in the wrong order, so then negative a squared. So plus e to the negative c squared. Then plus, let's see, limit as b goes to infinity of e to the negative b squared, and then minus e to the negative c squared. So you see why the c doesn't really matter, because these just go away. And honestly, I think you could actually make an argument from this, since they are literally the same limit, that can factor out the limit, do the subtraction, they must go to 0, so you can make the argument from that space as well. Alright, that's our first set of exercises from 8.8. Next time we will look at type 2 integrals. And those are similar, but instead of having infinite limits of integration, what they have is a discontinuity somewhere between the limits of integration. So it's a little bit different kind of situation, but a lot of the same rules we have come up with will be used again. So see you in that video.